Welcome back to another DSA tutorial. Today we're exploring one of the coolest self-adjusting data structures, the Splay Tree. If you want the best animated tutorials about data structures and algorithms, head over to our website, algopk.com. We've got interactive visualizations for everything. Let's dive in. So, what's a Splay Tree? It's a self-adjusting binary search tree invented by Slater and Tarjan. The key idea is simple but powerful. Every time you access a node, you move it to the root through a series of rotations called splaying. Why is this useful? Think about it. If you keep accessing the same elements over and over, they'll stay near the root. Frequently accessed elements become fast to find. It's like the tree learns your access pattern. Unlike AVL or red-black trees, Splay trees don't store any balance information. No heights, no colors, just the tree structure itself. This makes them simpler to implement and uses less memory. The catch, individual operations can be slow, O of n in the worst case. But here's the magic. Over a sequence of operations, the average time is O of log n. We call this amortized time complexity. Now let's understand the heart of Splay trees, the splay operation. When we splay a node, we move it up to the root. But we don't just do simple rotations, we use three specific patterns. First, zig. This is the simple case. When the node's parent is the root, we do one rotation. Left child, right rotate. Right child, left rotate. Done. Second, zig-zig. This happens when the node and its parent are both left children, or both right children. It's a straight line pattern. Watch carefully. We rotate the grandparent first, then the parent. This is crucial. If we rotated parent first, we just get two zig operations, which doesn't give us the same amortized guarantee. Third, zig-zag. This is the bent pattern. The node is a left child, but the parent is a right child, or vice versa. Here, we rotate the node itself twice, once around the parent, once around the grandparent. It's like an AVL double rotation. The key insight is that Zig-Zig and Zig-Zag both move the node up by 2 levels. We keep doing these until the node reaches the root. Let's see how insertion works. Step 1, insert the node just like a regular BST. Find the right spot and add it to the leaf. Step 2, splay the newly inserted node to the root. That's it. After insertion, your new node is always at the root. This might seem wasteful, but it means if you insert and then immediately access that node, it's instant. Watch the animation. When we insert 25, it first goes to its BST position, then we splay it up using zig-zig or zig-zag rotations until it becomes the root. Search is similar. Step 1, search down the tree like a normal BST. Step 2, if you find the node, splay it to the root. Step 3, if you don't find it, splay the last node you visited. This is clever. Even failed searches restructure the tree. The path you just traveled gets flattened, making future searches faster. After a successful search, the found element is at the root. Search for it again, O of 1. Deletion is a bit different. Step 1, splay the node to delete up to the root. Step 2, remove the root. Now you have 2 subtrees. Step 3, find the maximum element in the left subtree. Step 4, splay that maximum to the root of the left subtree. Step 5, attach the right subtree as the right child. The tree stays valid because the max of the left subtree is smaller than everything in the right subtree. Let's talk about why Splay trees are efficient despite having O of n worst case. We use a technique called potential analysis. Imagine each node has a rank based on the size of its subtree. The total potential of the tree is the sum of all ranks. When we splay, expensive operations, the ones that move nodes far, actually reduce the potential. The tree becomes more balanced. So even if one operation is expensive, it pays for future operations by improving the tree structure. The result? Any sequence of m operations takes O of m log n total time. That's O of log n per operation on average. Splay trees have some amazing theoretical properties. Static optimality, they're within a constant factor of the best static BST for any access sequence. Working set property, recently accessed elements are fast to access again. Sequential access, accessing all n elements in order takes only O of n time total, not O of n log n. Dynamic finger, accessing elements near each other is fast. There's even an open conjecture that splay trees are dynamically optimal, as good as any BST algorithm, even one that knows the future. When to use splay trees? Use them when you have locality of reference, some elements accessed more than others, memory is tight, no extra balance information needed, you want simple implementation, and amortized complexity is acceptable. Don't use them when you need guaranteed O of log n per operation, access patterns are truly random, or you're building a real-time system. Real applications include caches, garbage collectors, and network routers, where recently used data is likely to be used again. Code explanation. Let's look at the implementation. In C++, we define a node structure with key, left and right, and parent pointers. The parent pointer is important for splaying. The right rotate function takes node x and its left child y. We move y up, x becomes y's right child, and y's right subtree becomes x's left subtree. We update all parent pointers carefully. The splay function is the heart. We loop while the node has a parent. If parent is root, zig. If same direction is parent, Zig-Zig. Otherwise, Zig-Zag. Notice in Zig-Zag we rotate the grandparent first. Insert creates a new node, walks down to find its position, links it in, and then calls splay to move it to root. In Java, same structure but with proper OOP. Node is an inner class. We use null checks instead of sentinel nodes. The rotation logic is identical. In Python, clean and readable. We use none for no pointers. The splay method has clear if-else chains for the three cases. The AND operator makes the Zig-Zig condition readable. In JavaScript, modern class syntax uses const for the temporary variables in rotations. The logic is exactly the same. Find position, insert, splay. The key takeaways from all implementations are 1. Always maintain parent pointers. 2. In Zig-Zig, rotate grandparent before parent. 3. Splay after every operation. And 4. It's surprisingly simple. No balance factors needed. Comparison with other trees. With quick comparison. Versus AVL trees, AVL guarantees O of log n worst case. Splay is simpler, no height tracking. Splay better when access patterns have locality. Versus red-black trees, red-black also guarantees O of log n. Splay uses less memory, no color bit, and splay is faster for repeated accesses. Versus skip lists, both are randomized or amortized. Splay adapts to access patterns. Skip lists are easier to understand. And that's Splay Trees. Let's summarize. Self-adjusting BST that moves access nodes to root. 3 rotation types, Zig, Zig-Zig, and Zig-Zag. O of log n amortized time for all operations, great for workloads with locality, simple to implement, no balance tracking needed. The beauty of splay trees is that they adapt to how you use them. Access the same elements repeatedly, they'll be fast. Your access pattern changes, the tree adjusts automatically. Try the interactive visualization. Insert some nodes, then keep searching for the same one. Watch how it stays at the root. For more amazing animated tutorials on data structures and algorithms, visit algopk.com. We cover